All right, in this lecture we're going to talk about acid-base catalysis. This is very common in aqueous solution and probably quite important to all of you who are thinking about a biomolecular option. A lot of the chemistry that happens in living organisms it involves a lot of this acid-base catalysis. Okay, so I'm going to give you a few examples. So asparagine residues in proteins go through this degradation process. It's a post-translational modification where you start with the asparagine residue and it converts with an apparent rate constant K into an aspartate residue. Okay, so you can imagine that this has pretty big consequences. These uncharged residues are gradually becoming charged residues of aspartate, and that of course changes the way the protein matches its target. For example, if you're making a monoclonal antibody or something like that, you don't want these new charges to be popping up. One of the things that they have learned to do, initially on a rather empirical basis, was to store these therapeutic proteins in acidic solutions around a pH of 3. One of the reasons for that is that when you plot the logarithm of this apparent rate constant for the decay of these proteins, you see that the rate initially starts pretty high, drops as you approach pH of 3, then rises again, and then reaches this plateau, and then eventually turns upward again at a pH somewhere up above 8 or 9. Okay, so this puzzling behavior indicates that there's something rather complicated happening here, and that is acid and base catalysis. Okay, so we're going to go through in our lecture today and learn how to recognize signatures of acid catalysis and base catalysis from diagrams like this one. And we're also going to learn how to actually derive rate laws from proposed mechanisms. And hopefully, from the intuition that we establish by doing that, we can look at rate profiles like this and begin to formulate reasonable mechanistic hypotheses for what's going on. The other example I want to show is aspirin hydrolysis. Okay, so these are also pH dependent. You start out with acetylsalicylic acid. It reacts with water, again with an apparent rate constant K, to give you this ineffective phenol compound and acetic acid. And if I plot the logarithm of this K versus pH, I see a very similar situation. The rate constant starts out high. As the pH increases, I dip, passing through a minimum at around 2. And then I have this plateau, which corresponds to the pH in the rest of our body. The minimum around 2 happens to coincide with the pH of the stomach. And the consequence of this is that aspirin degrades slowly at the conditions in the stomach, and that helps it make it into your tissue with no fancy protection. Okay, so how does this relate to reaction orders, and what does it tell us about mechanisms? Well, really what you're looking at here is a reversed plot of the usual Van Hoff analysis, right? So recall that pH is just the negative of the logarithm of the H plus concentration. So when I move to the left on the pH axis, my H plus concentration is going up, my pH is going down. I'm plotting the log base 10 of my apparent rate versus a log base 10 of the H plus concentration with a negative sign. I know that this is giving me the reaction order. So when my slope is 0, it means that additional H plus doesn't affect this at all, and we say that we have a pH independent rate law. When my slope is positive, it means that as the H plus concentration is getting smaller, moving to the right along this axis, the rate is going up. So the H plus concentration is getting smaller, the OH minus concentration is getting bigger in solution. So we call this section here is going to be base catalyzed. When we look at a section like this, where the slope is -1, now the rate is going up. The derivative of this logarithm of K with respect to the logarithm of H plus is +1 here because I've got the negative sign coming through the pH right there. Okay, so this is acid catalyzed over here when you see the slope of -1 on this log K versus pH plot. Okay, so these are called Loudens rules. And they tell you how to interpret these features that you see in data. Okay, so when you see a downward bend in the log K versus pH profile, that's caused by a change in the predominant protonation or deprotonation state of species along your reaction pathway. So we're going to consider this reaction where substrate S goes to a product, and it's going to involve 2 steps. First, we protonate S to give us H+. Then the protonated species SH+ reacts to give me B plus H+. Notice that my H plus catalyst appears as a reactant and again is regenerated as a product, and so it is a true catalyst here. Also note that the equilibrium constant is written for the reverse process of the one that I wrote here. That's because when we talk about equilibria that are protonations and deprotonations, we usually work with the acid dissociation constant, Ka. So the reactant here we think of as the SH plus becoming its conjugate base and the free H plus concentration. So I'm going to start deriving this rate law by writing down that R is equal to K times the SH plus concentration. That comes from the rate of this elementary step that makes my product. Okay, now the first thing that I want to do is to rewrite S in terms of SH plus and in terms of the total amount of S in solution. So it's the sum of those two. All right, so I use my equilibrium relation here to do that, and I get a relationship here. I can now factor out the SH plus and solve for it. That's this expression right here. And then I plug that expression for the SH plus into my rate law above, and I get this for a final rate law. Notice that this now only depends on the total amount of substrate S, regardless of its form, and the H plus concentration. All right, so if I were to plot this, showing the log of the rate versus pH, what I would see as the H plus concentration becomes very large, Ka down here in the basement will become negligible, the two factors of H plus will cancel, and we will end up with just K times S total, right? So out here, the rate law, the rate is approximately K times S total, and it's independent of H plus. If I keep adding more and more protons, it doesn't make any difference. These things are I already have a predominant protonation state that corresponds to the SH plus species. If I move out to the right of my pH profile, now as I move in this direction, the H plus concentration is getting smaller and smaller. Eventually it gets smaller than Ka itself, and now I can basically ignore it, and I get a rate law that looks like K H plus S total divided by Ka. Okay, so over here, my rate law is approximately K H plus S total over Ka, like this. Okay, now counterintuitively, we're at the high pH region, which means that we have a basic solution, and yet we say that this is acid catalyzed because the slope is -1. Really think about it, that makes sense, because as we move to the left, we're increasing our acid concentration and the rate is going up. Okay, even though that is happening in a basic solution, I can still think about increasing or decreasing the amount of H plus. The key feature that I want to point out in this, of course, is that there's a downward bend here. These two things cross over each other at the point where the pH is equal to the pKa, or equivalently, where H plus is equal to Ka, and that corresponds to this downward bend. Notice what happened. Over here, the predominant protonation state was S, and over here, the predominant protonation state was SH plus. Okay, so that was this example of Loudon's rules, a change in the predominant protonation state. Let's see how it happens in the other direction. Okay, so now what we're going to do is let the unprotonated species S be the one that reacts to form P. Okay, similar mechanism, but now we're starting with a protonated SH plus. It's making the unprotonated S and freeing up an H plus. Then we have S going to form my product. Okay, with a rate constant K. So the rate law that we want to write down is K times the concentration of S. The amount of S I can now go through and solve using the same steps that we used before. I get this expression, I plug this expression in here, combine these two things basically, and I get a rate law that looks like this. Now, let's look at what happens here. As I move far to the left, I'm getting a very large H plus concentration. I can begin to ignore the Ka, and we get a rate that is inhibited by the presence of more and more acid, or equivalently, a rate that's base catalyzed. Okay, so the slope is +1 here, indicates that this is base catalysis. When I cross through this point, what happens is that H plus has now become smaller than Ka. I can now begin to ignore H plus, and the two Ka's cancel, and I get a pH-independent rate law that looks like Ks total. Again, we get this downward bend that happens right there where these two things meet. Okay, so those are examples of Loudon's rule for simple acid and base catalyzed processes. So we can explain these downward turns as changes in the predominant protonation state of a reactant. What about upward turns? Well, Loudon says that regions on the opposite sides in pH of an upward bend in this plot are going to correspond to different sequences of intermediates, i.e. to completely different mechanisms. I won't go through all the details here, but this is going back to this asparagine deamidation case where we saw that the profile looked like this. And if you look at this section 1 along this profile, it follows this pathway. And you're going through these intermediates where you have all this protonation up here. So these are all 3 protonated intermediates along this pathway. That's why it's acid catalyzed, is because the more H plus you have, the easier it is to form these protonated intermediates. So this is your acid catalyzed pathway, number 1 right here. And the other section, the base catalyzed pathway, 2, proceeds through a series of deprotonated intermediates. So these two are both deprotonated, and the more OH minus you have, or the less H plus you have, the easier it is to deprotonate these things. And that's why this is base catalyzed. Now, what happens in reality is that even out here at this pH, you still have contributions from 1, but they become vanishingly small compared to the contributions from 2. And likewise, 2 has crossed through 1 as we move far to the left. And then they sort of mix right here near this elbow. They're both making contributions to the rate at that point. So these are examples of Loudon's rules. You now know how to interpret things that look like an upward bend. These are changes in the sequence of intermediates and elementary steps, and downward bends in the pH versus rate profile correspond to changes in the predominant protonation state.